Hi everyone, today we're going to be doing chapter 7, the central limit theorem. So the central limit theorem basically gives us a way of taking any continuous distribution and looking at the means of samples, and then the sample of those means ends up being normally distributed if the sample size is big enough. All right, then we're able to make statistical inferences based on that, and you'll see how that we end up going in chapters 8 and 9, confidence intervals and hypothesis testing that uses the theory here from central limit theorem. So why are we so concerned with means? Because they give us a middle ground for comparison, and they're easy to calculate, right? It's easy to calculate the mean of a set of data. So the central limit theorem, or CLT, is concerned with drawing finite samples of size n from a population with a known mean mu and a known standard deviation sigma. So the theorem says that if we collect samples of size n with a large enough n, calculate each sample's mean, and create a histogram of those means, the resulting histogram will look like a normal distribution. So if the original population is normally distributed, we don't need a large sample size, because automatically the sample of means is then going to be normally distributed. If the original population is far from normal, n should be at least 30 for the distribution of sample means to be normally distributed. So that's the assumption we're going to make when it's not normally distributed, that we have to take a sample size of at least 30. So here's what the central limit theorem states. Suppose x is a random variable with a distribution that may be known or unknown. It could be any distribution. And mu sub x is the mean of that random variable, and sigma x is the standard deviation of it. So if you draw random samples of size n, then the distribution of the random variable x bar, we're going to say big X bar, is going to be the sampling distribution of the sampling mean. All right? So it's the distribution of every possible sample mean that could be obtained from a random sample of size n from the original population. So the mean of the sampling distribution, mu sub x bar, is going to be the same as the mean of the given distribution that we're operating from. Standard deviation of the sampling distribution, you take the standard deviation of the regular distribution divided by the square root of n, and then you have the standard deviation of x bar. So if x is normal, then x bar will be normal no matter how big n is. If x is not normal, then if n is bigger than or equal to 30, x bar will be normal. So x bar is normally distributed with a mean mu x and standard deviation sigma x divided by radical n, where n is the sample size. All right, that's a lot. So we'll crack into a few examples here and see how they work. We're basically going to be using the same calculator keystrokes that we used in the last chapter, where we're using normal CDF and inverse norm. So an unknown distribution has a mean of 45, so that's your mu x, and therefore your mu x bar too, and a standard deviation of 8. That's sigma x, so we're going to have to divide that by square root of the sample size, which we see is 30. So samples of size n equals 30 are drawn randomly. What is the probability that the sample mean is between 42 and 50? So first of all, we figure out what the normal distribution looks like for this sampling mean, and we get that it has a mean of 45. So that is this right here. There's your mean of 45, and a standard deviation of 8 divided by square root of n. So 8 divided by square root of 30, which turns out to be that 1.4606 number. So probability x bar is between 42 and 50. We use normal CDF from our calculator, and 42 is the lower, 50 is the upper, 45 is the mean, 1.4606 is the standard deviation, and we find the probability that the sampling mean is between 42 and 50 is really high. It's about 98%, right? 0.9797. Okay, you're going to see some problems in MyOpenMath where you got to go back and forth between the regular distribution x and the sampling distribution of means x bar. Okay, so it looks like I got a typo here, and that should have been X bar, right? That should have been X bar right there. So, make that correction in your notes as you go through. Okay. So the average number of miles in thousands that a car's tires will function is 73 with a standard deviation of 12. Suppose that 18 randomly selected tires are tested. So n is less than 30 in this case, right? N is less than 30. That means for the central limit theorem to work, the original distribution x has to be normal. All right, so we need to have that assumption in place this time. So my open math is going to ask you, is it necessary for x to be normal? In this case, it is, because the sample is less than 30. All right, so the distribution of x is going to be normal with a mean of 73 and a standard deviation of 12. And then x bar is going to have a mean of 73 and a standard deviation of 12 divided by radical 18, because 18 is the standard, or the sample size, and there you have the standard deviation of the sampling distribution. Okay, so if a randomly selected tire is tested, what's the probability that the number of miles in thousands before it will need to be replaced is between 70.6 and 73.7? So this is asking you not about the sampling distribution, it's asking you about the regular distribution. Randomly selected tire from that regular population of tires. So therefore we are using the 73 and 12 normal distribution, right? We're using this one right here, okay? The other one, and we come up with 0.1025 when we do the normal CDF on that one. So then what is the probability for the 18 tires tested to have a mean between 70.6 and 73.7? So now we're talking about that sample of 18 tires. So we're going to use the other one. We're going to use this one right here when we do our normal CDF. So we use that one with that different standard deviation. Okay. So as you can see, I go down here and I do normal CDF with those numbers. As you can tell, this is a bigger number, smaller standard deviation, right? So it's going to sweep in more numbers according to the empirical thing that we learned in chapter 6. So the 0.3997 is going to be the probability that that sample of 18 tires has, or it fails between 70.6 to 73.7 thousand miles. Alrighty? Okay, looks like we got one more. The amount of coffee, two more. The amount of coffee people drink per day is normally distributed with a mean of 14 ounces and a standard deviation of 4 ounces. Oh boy, I think I'm one of the outliers. Me and Mr. Sterling, right? Way more. For my LCC people, Mr. Sterling is a teacher at Churchill that I worked years and years with, and he drank a lot of coffee. All right? So, if 15 people are selected at random, find Q1, Q3, and the IQR of the average of the 15 coffee drinkers. First thing I got to do then is I got to figure out what the sampling distribution is. X bar is going to be normal with a mean of 14, and we're only doing 4 people, or 4 to 15 is the sample size. Excuse me, I couldn't get that out. So 4 divided by radical 15 is going to be our standard deviation of the sampling distribution, and there you have it. All right. We don't need to assume it's normal, because the amount of coffee people drink per day is already normally distributed, so we don't need to have that assumption that X is normal like we did in the last example. So remember, for Q1, 25% of the data's got to be less, so the left tail area right here is 0.25. Mean of 14, standard deviation 1.0328. So 13.304 is going to be quartile 1. Quartile 3, remember, is 0.75 in the left tail this time. Same mean, same standard deviation. And we come up with that number for our Q3, so 75% of the time the sample will result in 14.6966, the mean being less than that. That's what that's saying. So the IQR, subtract those two numbers, right? these two numbers, 14 minus 14.6966 minus 13.3034, ends up being that number right there. Okay, there's your IQR, interquartile range. Okay, last one. So this one ends up being the more tricky one in this section because it comes from a uniform distribution, so we're hearkening back to chapter 5. So a study involving stress is conducted among the students on a campus. The stress scores follow a uniform distribution with the lowest stress score equal to 1 and the highest stress score equal to 5. So X is a uniform distribution with between 1 and 5. So we calculate the mean by doing 1 plus 5 over 2. We got 3. Then the standard deviation, remember the formula for standard deviation of a uniform distribution. So we actually have to make that calculation, and I got 1.15 when I do that, radical b minus a squared over 12. So then from there, I know that the mean of the sampling distribution is 3 and the standard deviation of x bar is 0.1551. And you want to know then, what's the probability you pick 55 students and their stress is lower than 2.7. Okay, so we have to do normal CDF less than, remember we got to do the negative 1e99, that's like negative infinity, comma, 2.7 is the higher bound, and then 3 is the mean, 0.1551 is the standard deviation, let her rip, and you get 2.65%. Alrighty, so there we have it. That's chapter 7 in a nutshell. All right, have a great day. We'll see you later.